Hello. In this video, I'm going to go over word problems that we saw that were similar to the practice quiz that we encountered last week. Additionally, I want to talk about some other problems, other types of equations that you should be able to handle now that we're in Unit 3, Part 2, Lesson 2 of our college algebra course. In this first example, we saw this exact problem last week in our series of videos. So I'd like for you to read this problem and complete it again on your own. Try to do so without looking back at your old notes. Please pause the video now and resume playback in a moment to check your work. And here's that solution. In this particular problem, we had to solve for our growth rate first. So we recognize that half of the radioactive material is left after 5 days' time when we started with 100% of that material. So by solving for A, we could then use that A value inside of our growth rate or inside of our exponential growth formula as the growth rate. Our target was to see when or what X value makes the equation equal to 9. So we rewrote this exponential as a logarithm. And I think you could have gotten to this point. We could have gotten all the way to here without a calculator. And the only time that we needed a calculator in this particular example was right here when we actually executed this logarithmic command. So this question is fair game for both calc and no calc portions of the test. If I put this on a no calc portion of the test, this is the answer that I'm looking for. If it shows up as a calculator permitted question, then of course the answer in decimal values of days would work as well. For our second example, you should have seen this type of question in your Math Excel work. Now, we need to modify our exponential growth function just slightly in order to handle this particular problem. Because what we have is a thermometer that's being brought into a room that has a particular ambient temperature. In other words, the temperature of this thermometer is not going to settle out at 0, and it didn't start at 0. And so while we still have an initial value and a growth factor or growth rate and a variable, which most of the time is a variable in time, we've got this other variable called our ambient temperature variable in this case, and this essentially offsets our equation a little bit. So I do also want to make a note that this initial value C is also not relative to 0, but it's relative to B. And I'll show you a sketch of a graph in just a moment to make my argument there. So as we read through this problem, we're first told that a thermometer reads 5 degrees Celsius. Now, before I do much of anything, I'm just going to try to identify these numbers. And so this means that at time 0, the thermometer is reading 5. So f of 0 has to equal 5 in this scenario. It's brought into a room with a constant temperature of 38 degrees Celsius. Well, this is that ambient temperature that I was talking about just a minute ago. The room is 38 degrees. So while the thermometer is reading 5 degrees now, it's going to warm up towards 38 degrees. Some additional information is needed in order to solve this problem, and we are told in part A that the thermometer reads 16 degrees Celsius after 3 minutes. So the function evaluated at 3 minutes should be equal to 16 degrees. And with that preliminary information, we should be able to establish the function f of x and then be able to answer the question, what is the temperature at 5 minutes and at 10 minutes? So in other words, what is f of 5 going to be and what is f of 10 going to be? So those are our goals, to find f of 5 and f of 10, but before we can evaluate that, we need the function f of x. So if it were me, I would start at the beginning. I would start with that f of 0 equals 5 business. Now, again, I know that f of x is equal to c times a to the x power plus b, and we know a couple things at this point. We know that f of 0 is equal to 5, and we know that, well, we don't know the initial value. Again, that's relative to the b value, so we don't know that yet. We don't know our growth factor, but we do know that x is 0 and that our B value, our room temperature, is 38 degrees. Now here again, I know that f of 0 is equal to 5, but I didn't indicate that in this line. I'm going to indicate that here. I'm going to replace f of 0 with the number 5 because I know those two are equivalent. I also know that a to the power of 0 is equal to 1, and 1 times c is just c. Well, now I know that 5 is equal to c plus 38. Therefore, c is equal to negative 33. In other words, our graph at time 0 is starting 33 units below B. The next point that I'd like to consider is that f of 3 is 16. F of 3 is equal to 16. And f of 3 would be our c value, which we just determined to be negative 33, times a to the third power plus 38. Well, again, if 16 is equal to negative 33, a cubed plus 38, then I could do the math in order to isolate a. I'm going to subtract 38 to move that to the left side. I can divide by negative 33 after that's done, and then take the cube root in order to isolate this power of 3. And now after you've practiced this a bunch, and you've seen it in Math Excel certainly by now, you should be able to do all of this work in one step. I'll leave the arrows on screen just to remind myself of what was done. But as a recap, I subtracted 38 first. I divided that result by negative 33. And I took the cube root of all of that together. No need to reach for a calculator. I don't really care what 16 minus 38 is, and I don't really care what that result divided by negative 33 is either. That's just wasted effort at this point. We know that a is equal to this particular expression, and that's going to be good enough for me. So if we look at this modified exponential growth formula, we now have our c value, we have our a value, and we have our b value. If I need to answer question A and evaluate this function at 5 and at 10, I can do so. F of 5 is simply going to be negative 33 times the cube root of 16 minus 38 divided by 33. Sorry, negative 33. Raise that to the fifth power. I have no idea what that is, and I couldn't evaluate that without a calculator, but I've done all of this work so far without a calculator. The only time that I'll need the calc is right here to obtain these two answers. So let's set up f of 10 while we're at it. We've got negative 33 times the cube root of 16 minus 38 over negative 33. This time that's raised to the 10th power. And I can build that in the TI calculator pretty easily. We're starting with negative 33 times the third root of a fraction, 16 minus 38 divided by negative 33. And all of that is raised to the fifth power. So before I press enter, I'm going to double check. Does what I have on paper match what I've written into the calculator? And at first glance, that looks fine. And if I trust what I've written on the calculator or written on the paper, then I should be able to trust what I get back from the calculator. But this result doesn't look right at all, does it? So what did I forget? Ah, yes. The equation required the sum of 38 at the end. Hopefully you caught that mistake and was screaming at the screen as I omitted that. Let's go back and correct that. So I'll copy that down from before by simply highlighting it and pressing enter. Now to that I will add 38, and we'll try this one more time. And our T value, or X value in this case, the time needed in order to reach that temperature, strike that, let me say that again. After 5 minutes, the thermometer should read 21.2109 degrees. And now that we've correctly built that expression into our calculator, again, we can press the up arrow until it's highlighted to repeat it again. And we'll change this exponent of 5 to 10. And now after 10 minutes, the thermometer should read 29.4583. All right, so 21.2109 degrees Celsius and 29.4583 degrees Celsius. These two answers address the solution to part A. Now, if we're thinking about a graph here, let's just make a quick sketch. Actually, I think these axes are going to work better. So we have a horizontal axis, that's time, that was our x variable. And then f of x, our y-axis, was temperature. So we had temperature in degrees Celsius, and x was time. What we knew was that at time 0, the temperature was 5 degrees. And we also knew that the ambient temperature was 38 degrees, somewhere up here. So as you can imagine, the temperature is going to rise as we approach this leveling off point. So at time 0, we had a temperature of 5. We had an important point here of 38 degrees. And after 5 minutes, the temperature jumped up pretty significantly. It was about 21 degrees. And then after 10 minutes, it was about 29 degrees. And while my scale may be off here, you can start to see a bit of a trend that's occurring. In fact, we could probably test some other data points to see if this is truly what's happening. But we're starting to see a graph that takes on this particular shape. Now, that wasn't really asked for us to do in part A, but it's good to consider. It's always good to be mindful of the entire equation. So let's go ahead and answer part B, and we'll just show this result on a graphing calculator. So back on the calculator, since I have a calculator page open, I need a graphs page open too. So I press Control Dock, and I'll instruct the calculator to open up a graphs page. On this function, we'll go ahead and write the equation we established just a minute ago. Negative 33 times the cube root of the fraction 16 minus 38 over 33, negative 33, to the power of x, and we add to that 38. I don't want to forget that 38. We'll press enter. We don't see much of what's happening now, but I do know that I tested some points between 5 and 10. Let's go ahead and just change our x-axis. Let's run it out 30 minutes. So we'll go from negative 3 to 30. Again, I like going leftward by about 10%. So if we're going to the right 30, I'll go to the left 10% of that, which is 3. And I'll tap OK. I still can't see the rest of the graph, but once I've established my x values and I'm happy with them, if I jump into the zoom settings, zoom number 4, I can choose option A to fit the y-axis. And that usually does a nice job of adjusting our vertical axis. And we can see that that trend line, that pattern that I sketched just a minute ago. To really make this stand out, if I press the tab key and say that f of x is equal to 38, this was that horizontal line that we can definitely see that our function is approaching now. I think I can drag this to the right. You'll notice that this is an asymptote. The blue line doesn't ever cross that red line, and technically it doesn't touch it either. It looks like they're right on top of one another, but they are not touching at this point. In Math Excel, you'll likely have to select a graph that matches this blue one out of the options on the screen.